Alright, so welcome to the fourth data reduction for the semester. For this one, it's going to be aerodynamic forces on immersed bodies. So unfortunately, all of you couldn't do this lab at school, which kind of sucks because this is, I think, the best lab, or the best experiment for this lab. I think it's pretty interesting to actually measure the drag and the lift on some of these objects, but it is what it is. So I hope the video that I uploaded on titanium helped you out to get an idea of what we were going to do in this lab, at least for finding the drag and lift on an airfoil. So let's check out our data reduction. The first thing we have to do is calculate the actual airspeed for this lab. So we're going to convert that to meters per second, and then we're going to graph that against the reading that we have from the lab directly, which is in miles per hour. So just like in lab 3, we were adjusting the flow rate with the rotometer, but we had to measure the actual flow rate using our graduated cylinder and measuring the time it took to fill it. So in this case, we're going to go to Excel, and we're going to have some manometer readings for the static pressure and the stagnation pressure, and then we're going to get our our velocity that way. Okay, then we're going to measure the drag on a sphere and hemisphere. Then for the airfoil, we're going to find the lift coefficient for the airfoil. We're going to do that for different angles of attack and different airspeeds. So for this, we don't have drag data. So if we go here, we have lift data, but we don't have drag data, so we're only going to do it for the lift. Okay, the next thing is we're going to look at the pressure distribution on this same airfoil. So we had pressure taps along the top and the bottom of the airfoil. In this case, we're only going to look at the pressure on the top of the airfoil for different angles of attack and different airspeeds. And then we're going to plot that against the non-dimensional location. So for that, we're going to take the location of the tap and we're going to divide it by the chord length for the airfoil. Okay, and then the last thing we're going to do is look at the pressure distribution on a cylinder. So for that, we had pressure taps as well. Let's go up really quick. It looked like this. So we had all of these pressure taps. So we're going to plot that pressure distribution against the angle theta here. And then we're also going to plot the theoretical pressure distribution and compare that to what we actually measured. And we're going to do that again for different airspeeds here. We don't have this data at the end here. My guess is this lab, for this data that I have, I'm guessing they didn't have enough time to get to it, so because this is a pretty long lab if you actually did it. So that's it's actually not even in here, so I don't know, maybe they were doing this at one point and they decided to take that part out of the lab. I'm not sure. So anyways, that's all we're going to do today. The error analysis here, this is I think it's a differential kind of error analysis, and I won't have you do that. And then I'm going to quickly touch on this too, the review questions. From now on, I want you guys to incorporate these review questions into what you would already write in your discussion section. So you should already be discussing the results that you have in the lab, but you should incorporate all of these questions to better support your conclusions that you're making on the results. Okay, so anyways, we'll get started now with the data reduction. Okay, so what I've done here is I've started this out like every experiment. I've cleared the memory, I've specified some constants here, and then I've converted some of my units here. So you can read through these sections yourself, they're pretty self-explanatory. Okay, then I've initialized my arrays. So these first three lines, they're for the lift coefficient for the airfoil. So the first one is for closed slats and flaps. The second one is for open slats and closed flaps. And then the third one is fully open. So the flaps are open and the slats are open. So I have zeros of 6, 3. So if we go to our data, I have 6 angles of attack here. And then I have 3 different airspeeds. And then again, we're doing this for the lift. We don't have the drag data. Okay? And then again, we're doing that for all configurations of the airfoil. The second thing I have here is the drag coefficient for the hemisphere and the sphere. So we have the drag for the sphere and the hemisphere, and I have 5 readings for the velocity, and then I have the sphere and then the hemisphere, so that'll just be zeros of 5, 1. And then I'm getting the Reynolds number for the sphere and the hemisphere as well. Okay, so that's going to be 5, 1 as well. The next thing we have is the pressure coefficient on the airfoil. So we have 3 different angles of attack here. So for this, I'm writing out 3 different lines for the different angles of attack. The first one is at 0 degrees angle of attack. The second one is at 10. And the third one is at negative 10 degrees for the angle of attack. Okay, so for this we have zeros of 11, 3. Let's go to our data sheet here. Okay, so here we are. We have 11 taps here, and we have 3 different airspeeds. And then again, remember we had the 3 different angles of attack, but what I've done in MATLAB is I have all of those kind of separated, kind of like we did with the different flap and slat configurations for the airfoil. Okay, the next thing I have is the pressure coefficient for the cylinder. So we have the right side of the cylinder, and then we have the left side of the cylinder. And then I have zeros of 18, 3. So for that, here we have the right half of the cylinder, and then we have the left half. Then I have 18 taps here, and then I have 3 airspeeds. Alright. Okay, so what I've done now is everyone's favorite part. I've imported and I've sorted all of the data. So for this section, you can basically just write it down like I have it. It should be the same besides table 6A, 6B, and 6C. I think for you, this was formatted a bit differently here, but you can get it into this format that I have. Okay, then I sorted the data into separate arrays. So the first one is the velocity for the wind tunnel in miles per hour. Okay, so that was from A that I made here. So I want to get all of the rows in this first column. And basically, if I go over to Excel, that's going to correspond to that selection right there. Okay, the next thing I've done is I've calculated the velocity for each wind tunnel in meters per second. So if you look at the code here, it's a bit different. So let's go to our handout that we had. So for the first wind tunnel, we're using a gauge fluid of water. And for the second wind tunnel, we're using a gauge fluid of oil. Okay, so that's going to change our equations a bit once we solve for the velocity right here. Okay, so we need to use a gauge fluid of water for the first one. And then for the second, we're going to use a gauge fluid of oil. And then it also looked like for the first wind tunnel, we didn't have an inclined manometer, I don't think. I'm just kind of looking at the data that I had. So you'll see for that, we're just doing 2 times, here I'll put this over. We're doing 2 times gravity times our gauge fluid multiplied by the density of water divided by the density of air. We're going to convert that to meters. And then we're multiplying it by a change in height that we have, which, let's go back to Excel now, which is going to correspond to our static pressure head and then our stagnation pressure head. Okay, so we're doing static minus stagnation right there. We're taking all the rows in our second column, and we're subtracting it by all of the rows in the third column. Okay, and then for wind tunnel 2, now we're going to use the specific gravity of oil, and then we're going to now multiply it by sine of phi, and then multiplied by our conversion again to meters, and then multiplied by our static pressure head minus the stagnation pressure head. So if I go back here, we see delta L sine of theta. In this case, I have phi. And this sine d, that's using sine in degree mode. Okay, so it's going to convert it to that. Okay, and then what we have here is the drag on the hemisphere. And we have the drag on the sphere, so that's just pounds to newtons. Remember, for our lab here, we basically recorded the drag somewhat directly. We just had to subtract our offset. So we did the total drag minus the offset drag, which is from our stand, and then we were able to get the drag on the sphere itself. So that's what we're calculating right here. Okay. And then we have the lift on the airfoil, and that's for all of our configurations. So just like with the drag, we were able to kind of measure that directly. So for that, we're just going to convert that to newtons. Alright, and then what I've done here is I've just converted the measurements to SI units. Okay, so quick update. What I've done here is I've changed this to B4 minus B3. So what I had in the beginning was B4 minus B1, but what we should do is take this fourth column and subtract it by the third column right there. So that's for the drag on the sphere. And then also here, I kind of talked about this last time, but what I've done is I've added this specific gravity for water here, and I've changed this to specific gravity underscore O for the specific gravity of the oil. Okay, so just make those corrections and then you'll be good to go. Okay, so now what I have is I started the data processing section for our experiment. So I have question 1 and I have question 2. So question 1, this is for the velocity of the wind tunnel. We're going to calculate the actual airspeed, which we've already done up here in those two lines. And then we're going to plot the actual airspeed versus the meter reading that we have. And we're going to fit the data with a linear function. Okay, so what I've done here for wind tunnel 1, I'm using the polyfit command. So I can use a best fit curve here. It's going to be a linear curve. Okay, so I have A equals polyfit. Okay, and then I'm going to use the velocity of the wind tunnel. Okay, so that's going to be in meters per second, or sorry, miles per hour, and that'll be on the x-axis. And then I have our calculated velocity. That'll be in meters per second, and that'll be in the y-axis. Then I have comma 1, so we have a linear curve. Okay, so now I'm going to create the x and y domain. So I have x2 equals lens space of 10 to 40. That'll create a domain for us for the domain of 10 to 40 miles per hour. And then for y2, I'm going to evaluate that using the polyfit command that I created up here and the x-axis data that I have right here. Okay, and then that'll create our y domain. Okay, and then I've used similar logic for the second wind tunnel down here. Okay, so for question 2, the drag coefficient on a sphere and hemisphere. So what I have here is the drag coefficient on the sphere, the hemisphere, and then the Reynolds number that we also need to find. Okay, so the Reynolds number, that's just rho v d divided by the viscosity of air, so that's pretty simple. If you look at my code here, I have the velocity for the first wind tunnel. So for this lab, for the data that I have, I think the groups they split up. So the first group for wind tunnel 1, they were tasked with finding the drag coefficient on the sphere and the hemisphere, and then a few other things in the lab. And then wind tunnel 2, they had to do other parts, like I think, we'll see later on, but I think they had to do it for the cylinder here, so that's why we're using the velocity for the first wind tunnel here. Okay, so we need to find the drag coefficient. So that's just 2 times the drag that we recorded in the lab divided by the density of air multiplied by the velocity of the first wind tunnel squared, and then multiplied by the cross-sectional area of the sphere. Okay, so for our for loops here, I have for I equals 1 to 5, and I have for j equals 1 to 2. So we have 5 readings here for the 5 velocities that we have, and we're going from 20 miles per hour to 40 miles per hour. Okay, so if we look here, I'm going to iterate, so I have 5 values for each drag coefficient and for the Reynolds number. And I'm iterating on I as well for the drag that we had for the sphere and the hemisphere. But for the velocity, you see I'm iterating on j, where j equals I plus 2. So again, here we're starting from 20 and we're going to 40 miles per hour. But the velocity data that we have is from 10 to 40. So what we're doing, where 10 is 1, and this goes from 1 to 7 basically for the rows, we need to start at 20 miles per hour, not 10 miles per hour. So we're going to start from j equals I plus 2. So in this case, again, if we want to start at 20 miles per hour, and I was 1, then j equals 1 plus 2, j equals 3. So we're going to start on this third row right here at 20 miles per hour, and then we're going to go all the way up to 40 miles per hour. Okay, so this is basically just to select the data that we want to get. Okay, so that's it for question 2. Okay, so for this data reduction in this lab report, I'm going to have you work on question 3 by yourself. Okay, if you have issues, you can contact me and we can work them out. But the logic that we're going to use in question 3 is similar to the logic that we're going to use here in question 4. And it's similar in logic for what we've been doing in all of these data reduction videos. Okay, but I don't want to hand, all of this out to you because, yes, this isn't a MATLAB class, but you also need to know how to kind of parse and process your data by yourself. Okay, that's a valuable tool that you need to have. So for question 3, just to go over again, that was for the lift coefficient on the airfoil. So we're doing that for different angles of attack and for 20 miles per hour, 30 miles per hour, and 40 miles per hour. And we're also doing that for our different flap and slat configurations. Okay, so let's get started on question 4 though. This is the pressure distribution on the airfoil. So for this, again, we had taps going along the airfoil right here, so we could get the pressure. So for this, we're going to use equation 2.16 here. And what I've done is I've already kind of plugged in for the static pressure and the free stream pressure. Okay, so just make sure you kind of type all of this out here. So F12, that is our free stream pressure. If we go here, this is going to be F12 right here. So we've imported, what we've imported is all of this data, and then we're going to get that free stream pressure right there, which is all of this data, all of that head data. Okay, so let's talk about the for loops that we have here. Okay, so we have for I equals 1 to 11. That's because we have 11 taps. Again, we imported all of this, so we have our 11 taps here. And then we have for j equals 1 to 3, because we had 3 airspeeds. We have 20, 30, and 40 miles per hour. And we also had 3 different angles of attack, 0, 10, and minus 10. So instead of iterating for that as well, what I've done is I've written out a line of code for each of these different angles of attack. So CP is 0, 0 is for 0 degrees, CP 10 is for 10, and CPN 10 is for negative 10 degrees. Okay? But we have airspeeds of 20, 30, and 40 miles per hour. If we go to where we calculated our airspeed, we're going from 10 to 40 miles per hour, and we're going in different intervals than we have here. We have 10, or we have 20, 30, 40, so we're going in intervals of 10 miles per hour, while here we're going in intervals of 5. So I'm going to start at 20 miles per hour. So what I'm going to do is I'm going to have k equals 3 plus j minus 1 times 2. So let's take the example that I want to start at 20 miles per hour. So that'll be k equals 3 plus j minus 1 times 2, where j is 1. So then k equals 3 plus is 0, basically. So k equals 3. That's going to start us off at 1, 2, 3 at the 20 miles per hour. Then we have to go to 30 miles per hour. So now j equals 2. So k equals 3 plus 2 minus 1 times 2. So k equals 3 plus 2. Yep, I can do math, believe me. Okay, so then k equals 5. So we're going from 1, 2, 3, 4, 5. So now we're at 30 miles per hour. Okay, and then you just do that again for 40 miles per hour. And then I have J0, J1, and J2. Okay, so for this, now we need to think about how we're going to collect the head data that we have. Okay, so J0 is J plus 1. So let's keep in mind I imported all of this data. Okay, so J1 is right here, this axial position column. Okay, but for the angle of attack of 0, I want to start in this column right here. I want to start in the second column. So I'm saying J0 equals J plus 1. So if J equals 1, then J0 equals 1 plus 1. J0 equals 2. We're going to start collecting this head data on the second column that we imported. And again, that's for an angle of attack of 0 degrees. So for all of this, I'm using J0 here and J0 here. And then we're using similar logic for the other lines of code. So for the angle of attack of 10, now I want to start in this column. So I have J1 equals J plus 4. Let's say we're starting for the first fan speed of 20 miles per hour. So J1 equals 1 plus 4, J1 equals 5. So we're going from 1, 2, 3, 4, 5. We're starting on this fifth column right here. Then we have, then we have all of this here, and then you should be good to go, okay? Okay, so I ended that quite abruptly. You could probably tell I was a little confused at what I had here. So what I've changed here is these values here. So I should have J1 for this angle of attack of 10 degrees, and I should have J2 here. So we have J0 all in this first row, then we have J1 all in the second row, and then J2 all in this third row. And because we need that pressure data for each of those different angles of attack as well. So this is like F12, J0. This is F12, J1. And then this is F12, J2. Okay, so just make sure you have this code, this updated code. Okay, and then for this question, we need to plot our pressure distribution against the non-dimensional location. That's x divided by c, where x is the axial tap location and c is the chord. Okay, so for that, we're just doing this equation here, where we're taking all of our tap data from 1 to 11, for all of that axial position data that we have here. So that'll be all of the rows in the first column, rows 1 to 11 in the first column from all of this that we imported. So we just want this stuff here. Then we're going to convert that to meters, and then we're going to divide it by our chord length that we've already defined up top here. Okay, so we're just going to do that. And now we're done with question 4. So for question 5, we have the pressure distribution over the circular cylinder. So we're going to plot Cp versus theta, and then we're also going to have a theoretical pressure coefficient. So we're going to be using basically the same formula that we used up here. It's going to be, a little different for the data that we're taking. But other than that, it's pretty much the same. So we have, for I equals 1 to 18, we have 18 taps here, right there. And then we have for j equals 1 to 3, because we have 3 airspeeds, 15, 20, and 25. Then we have k equals 2 plus j minus 1 times 1. So this is similar to what we did in question 4. So we have airspeeds at 15, 20, 25. So I need to get 15, 20, and 25. So let's start at 15. We'll do k equals 2 plus j minus 1 times 1. So k equals 2 plus 1 minus 1 times 1. K equals 2. So we're going to start at 15. Then we'll get 20. And then up to 25. Now, of note, so let's go to the table here. This is what we have. We have 15, 20, and 25 miles per hour. If we go to the PDF, it says 20, 30, and 40 miles per hour. So, I don't know if this is really 20, 30, and 40 miles per hour. I'm going to assume not. I'm going to assume that this is 15, 20, and 25 miles per hour. So that's just something to keep in mind. I'm just going to assume it's that. Okay. And then just like we did up here, we have J0 equals J plus 1. We imported all of this. So I want to start collecting for the right half of the cylinder. I want to start collecting basically in the second column. So if j equals 1, then j0 equals 1 plus 1, j0 equals 2, I'll start collecting data here. For the left column, I want to start collecting data here. That's 1, 2, 3, 4, 5. So if j equals 1, j1 equals 1 plus 4, j1 equals column 5. Okay, like I said, very similar logic to what we had in question 4. Now we need to set up our domain. So first I have theta equals g. So this is g, this is what we imported. All of that. And I have from rows 1 to 18, comma 1. So the first column and then rows 1 to 18. Okay, now all of this stuff, these last 3 lines, this is for our theoretical stuff. So TT, that is our theoretical domain from 0 to 360 degrees. That'll be used for our plot. And then TT2 is a lens space from 90 to 450. So so for that, that's still 360 degrees, but I've kind of shifted the domain, where really I'm shifting this pressure coefficient here, where if you calculated this, it would start at -3, and it would end at -3 as well, where we're going to see this kind of sinusoidal kind of plot. So I want this to match up with our experimental data for the kind of phase that it's on. So that's why I'm using TT2 for my calculation in here. This will make more sense once we actually do the plot, when you can see it. Okay, so just make sure you have all of this stuff as well. And now we're finally ready to go ahead and plot. Okay, so I have question 1 and question 2 for the plots now. So the first one is for the wind tunnel. So again, we're plotting the measured wind speed. That's in miles per hour. And then we're going to plot that against our calculated wind speed in meters per second. And we're doing that for both wind tunnels. And then I also have here, this is basically our linear curve fit that we have. Okay. And then make sure you have a legend. A lot of you didn't have legends on your graphs. That needs to be in there. Make sure you have units on your labels. And then you don't need a title in the figure here, but you need to have a figure caption at least. And you can actually, put that in a word. Okay, question 2, drag coefficient on a sphere and hemisphere. So we have to plot that against the Reynolds number that we calculated. So I have Reynolds number against the coefficient of drag for the sphere, and then Reynolds number for the coefficient of drag for the hemisphere. So if we run those, here's our coefficient of drag for the hemisphere and the sphere, and I have a legend. And this isn't blocking any of the plots. You can move this around and then save it, or you can actually code out the placement where you want the legend as well. Okay, and then we have our wind tunnel plots. So for this, see, it's kind of blocking it, so I would put it down here, or up here, wherever. Okay, so then we have our plots there. Let me show you how to set the position as well. Okay, so we're going to do it like that. I can't type as well when the mic is blocking me. Yep. Okay, now we have it set. See, it went down here automatically, but I can still move it around if I want. But typing that out makes it nice and kind of centered, in this corner. So you can do that as well. Okay. Okay, so I have question 4 here, the pressure distribution over the airfoil. So I'm only going to do this for 20 miles per hour, but you still need to do it for 30 miles per hour and 40 miles per hour. Make sure you do that. Just because I don't include all of the graphs in my video here doesn't mean that you don't need to do them all. Some of you did that in the last lab report. Okay, so I'm doing plot. I'm plotting the dimensionless location against the pressure distribution for each angle of attack, and this is for 20 miles per hour. So this part right here, that's our pressure distribution or pressure coefficient at 0 degrees for the angle of attack. I have this (1), and that's corresponding to my 20 miles per hour. So if I go here, CP00, we have all of our 11 taps, and then we have 20 miles per hour, 30 miles per hour, 40 miles per hour. Okay, and then I have a legend once again. If I run this, now I have this graph here. Okay, so now we have question 5, the pressure distribution over the circular cylinder. Again, I'm only including one graph in this video, but you have 2 more to do. And I also put a little note here that our data is for 15, 20, and 25 miles per hour, allegedly, even though the data reduction shows that it should be for 20, 30, and 40. Okay, so I'm plotting the left cylinder, the right cylinder, and then the theoretical cylinder, and this is for 15 miles per hour. So if I go to CPL, again we have 15, 20, and 25 miles per hour, and then we have all 18 of our taps. Okay, so if I run this right now, I get a weird looking plot. So what I have to do is I need to shift my left data by 180 degrees. So I'm going to do theta plus 180. If I do that and I run it again, okay, now let's run it. Okay, so now I have a plot that looks like this. Okay, now this looks a little bit better. You know, we still have issues here that you're going to discuss in the report. But yeah, and then I have my theoretical plot on black and this black dashed line. And then again, you want to adjust your legend. So here, I mean, I guess it's fine. It looks a little weird. I would maybe make this plot, the axis, a bit bigger so I could put in the top rate. So you can adjust the axis using this line of code here. And I think you can also adjust the size of the legend as well. So if you want to, make this a little smaller, you could do that as well. Just make sure that I can still read it. Okay? So again, you're going to do this for 20 miles per hour and 25 miles per hour. Alright, so that's it for this lab. Hope you enjoyed, and I'll see you guys next time.